All right, today we're going to look at some other ways to solve uh, using universal law of gravitation. So today we're going to look at how to determine the gravitational acceleration, the mass of a planet, or the radius of a planet. So if we look at Newton's universal law of gravitation equation, and we have forces big G m over r squared. This used to be d squared, but now it's r squared. The reason is we're talking about the force of attraction on the surface of the planet. So we would then be looking at the radius for the distance that that object is away. The little m would be the mass of the object, and the large M would be the mass of the planet. Well, if we're talking about the force due to gravity on the surface of a planet, we call that weight. So that gravitational force can be then written as mass times gravitational acceleration. We've done that before. That's the definition of weight. And if you notice, the mass and the mass, those are the same mass. It's the mass of the object. So those two will cancel to find then the gravitational acceleration and how it's dependent upon two things. It's dependent on the mass of the planet and the radius of the planet. So if we look at Earl, and he's at his desk, and we know that this is the radius of the Earth and the mass of the Earth, we're going to calculate his acceleration due to gravity. Now, most of you could say, well, I know what his acceleration due to gravity is. Based on he's on Earth, it's 9.80 meters per second squared, and you would be correct. But we want to calculate that. So we're going to take this equation, and we're going to substitute. There's big G. It's a constant. The mass of the Earth we got from right there, and the radius of the Earth. Make sure you square it. When I do this in my calculator, I typically do the denominator first. So I plug this value in, I hit squared. To move it to the denominator, I hit the 1 over x key, or x to the minus 1 key, and then I multiply by the items in the numerator. And when we do that, we should get little g to be 9.80. To get meters per second squared, if we look, we have meters squared divided by meters squared. Those cancel. Kilograms squared in the denominator times kilograms leaves a Newton per kilogram. So how do we get a meter per second squared? Well, a Newton is a kilogram meter per second squared. And if we divide that by kilograms, so a kilogram meter per second squared divided by kilograms would leave you with just meters per second squared. Number two, we're going to look at what we did with the substitution method. We're going to apply it using this equation here. So if we know the gravitational acceleration on Earth is big G times mass of Earth over radius of Earth squared, and we know that the gravitation acceleration on the Sun is G mass of the Sun over the radius of the Sun squared, we want to compare those two accelerations. So let's look. What is this saying? The mass of the Sun is or equals 333,000 mass of Earth. So we're going to do a little substituting for mass of the Sun. It's going to be 333,000 ME. Let's see if we can figure out what's going to go in for RS. Good. Hopefully you see that the radius of the Earth, or radius of the Sun, equals 109 radius of Earth. So when we plug those two in, it looks like this. Again, we're substituting for mass of the Sun and radius of the Sun. If we move these items out front, look what this term is that we have left. Does this look familiar to something we've already written down on our page? Well, it should look just like this, which is equal to the gravitational acceleration on Earth. And if we use our calculator to solve this, this is telling me that the gravitational acceleration on the Sun is 28 times the gravitational acceleration on the Earth. So if you were to plug in 9.80 meters per second squared into this, and you multiply it by 28, it's roughly 275 meters per second squared. That is quite the acceleration. So in 1 second, you would actually fall half that distance from rest. So if you fell off, if you're on the Sun on a cliff and you were to jump or step off the cliff, in 1 second you'd then be moving at 275 meters per second, and you would have fallen 137.5 meters in that first second. That's pretty fast. That is some acceleration there. The human body can only handle probably 3 G's sustained, 8 or 9 G's for a short period of time before you black out. Air Force pilots actually wear special suits to prevent that, that actually squeeze your legs to return blood flow back to the heart and brain. If you pull too many G's, then blood actually leaves, is not able to return back to the heart. Your heart doesn't pump hard enough to get it back. So this would probably kill you, accelerating at that many G forces. So anyway, that's what you've got. You've got some homework problems to go along with that, but basically it's plug and chug, solve for one of these variables, and then plug in your numbers that it gives you.